Hi, everyone. Welcome to our next GoFly Master Lecture in our Master Lecture series. It's my pleasure to have Royce Snider here with us today. As you all know, we are so pleased to have Boeing as our grand sponsor for the GoFly Prize, and we are joined by corporate sponsor Pratt & Whitney, as well as over 20 aerospace and STEM organizations around the world. And as I mentioned today, we have Royce Snider. He is an associate administrator of the Bell ODA and the unit member delegated to recommend FAA Acoustical regulatory approval for Bell products. He serves as a consultant for Bell programs, represents the company on the ICAO CAEP Working Group for the maintenance of international aircraft noise standards, and is responsible to assist the development of regulations for innovation products, including UAS package delivery and air taxis. He previously served as program manager for the NASA Bell Tilt Rotor Test Rig and chair of the Acoustics Technical Committee of AHS International Vertical Flight Society. Royce has authored multiple technical papers and was recognized with the Best Acoustics Technical Paper in 2013 at AHS International Forum 69. He received his Master of Science in Aerospace Engineering from George Washington University in Washington, D.C., and his Bachelor of Science in Engineering Physics from Southwestern Oklahoma State University. So thank you, Royce, so much for joining us today.
Thank you. Hello, everyone. I'm going to share my screen. Okay, how does that look?
Looks great, thank you.
Okay, thank you for that introduction. I would like to thank GoFly for the opportunity to present a master lecture. It truly is an honor to be asked to contribute in this way. When I met Gwen, I shared with her my background and responsibilities at Bell. And I also reviewed the previous master lectures that have been presented to GoFly. We decided that where I could best contribute is the regulatory noise considerations for urban air mobility and unmanned aircraft systems. I would like to point out at least a couple of master lectures previously presented to GoFly. There was a very good lecture on rotary wing noise presented by Drs. Stephen Rizzi, Douglas Nark, and Nicholas Vodny at NASA Langley. Georgia Tech's Marilyn Smith discussed some rotary wing aerodynamics and aeroacoustics analysis considerations. Those are two presentations that should probably be considered prerequisites here. If you haven't seen those before, please give them a look. The rotary wing noise lecture especially discussed the different noise sources, generating mechanisms, analytical modeling, noise mitigation that would be relevant to these types of vehicles that we're all interested in and bring us here today. So I highly recommend that. Please let me start out by saying, on behalf of Bell Flight, I want to congratulate the 5 teams that were recently selected to receive the Phase 2 Design Awards. In alphabetical order, their teams Roxo from Russia and Latvia, Dragonair, Florida, US, Silver Wing Personal Flight from the Netherlands, Texas A&M Harmony, from Texas in the US, and finally Trek Aerospace in California from the US. Their vehicle concepts are shown here, the personal flying devices. Each of these teams has demonstrated significant accomplishments towards the GoFly technical objectives. If you haven't seen the 1-minute videos that are on YouTube, they are very much worth your time. I'm sure GoFly had to make some difficult choices in its down select from a competitive field in phase one down to phase two. So for the 5 teams represented there, please accept our congratulations for what has been demonstrated so far. And these are significant accomplishments, technical advancements, and I offer you best wishes as you proceed to the phase 3 flight demonstration. So that brings me to the agenda for today's lecture. And let's start with the so what. Why should regulatory noise considerations matter to a GoFly participant? Well, whether you are a GoFly participant that is developing a personal flying device, or if you're an established manufacturer that's designing a larger passenger vehicle like what I have depicted here, somewhere out there in the future, there are looming noise requirements for unmanned aircraft systems and urban air mobility type of vehicles. So let's take this opportunity to discuss how those requirements are emerging here. So I'm going to start with emerging noise requirements. Again, the so what. I'm going to do a quick review of the GoFly noise price, at least my understanding of it. I'm going to offer GoFly the opportunity to correct any misperceptions I have. And from there, we're going to roll right into how a manufacturer would be demonstrating noise levels if they were certifying an aircraft. I think it's interesting and informative to compare and contrast the GoFly noise prize versus how it's done in noise certification, in the noise certification world. And from there, I'm going to discuss several items, the noise limits, procedures. We'll briefly touch on international standards, some preliminary UAS noise measurements that the FAA has obtained. I think that these will be relevant to most of the UAS and UAM type vehicles that GoFly participants are interested in. So again, let's start with the so what. Currently, the FAA authorizes small unmanned aircraft systems that's specifically designed for UAS that are less than 55 pounds. And they authorize it under 14 CFR Part 107. And for these small UAS, it is prescribed that the operator maintains visual line of sight with the UAS. Flight is not allowed over people. It's daylight ops only. Obviously, the small UAS yield to aircraft, see and avoid types of operations. The max ground speed for these types are 100 miles per hour. Max altitude is 400 feet AGL to avoid any issues with other aircraft, larger aircraft. Considering the rapidly changing technologies, the FAA is allowing these deviations for small UAS. And likewise, considering the weight and power limitations that I've described here, the environmental compliance, like noise, has been provided by basically exclusion. Noise is excluded from the certification for these, specifically these types of UAS. So really there are no noise requirements for small UAS less than 55 pounds. It should be noted that in Europe, EASA has proposed small UAS noise limitations. My understanding is that right now, those proposed limits for small UAS have not become law yet. I know that there are some petitions in Europe contesting at least the way that those limits are being put in place. But that's my understanding now. So that kind of gives you a background for the very early entrant into this market space, the very small unmanned aircraft systems. As we move into the larger weight class of vehicles like unmanned aircraft systems, just larger UAS, and then the personal flying devices that GoFly is developing, and then some of the larger urban air mobility vehicles. What we are learning is that the FAA will likely impose noise requirements for UAS and UAM type of vehicles. I should note it is unclear if 55 pounds is the right threshold to impose noise regulations for UAS. My understanding is that is under consideration, whether 55 pounds is the right threshold, or perhaps they would extend that a little further. My understanding is right now, I don't believe the FAA is getting a lot of noise complaints or noise issues yet from these types of vehicles. So that's to be determined. We are learning that Part 36, or also the harmonized ICAO Annex 16, those regulations are probably what will apply to these types of vehicles. It'll initially be based on best fit, and then adapting the requirements for existing categories. So a new manufacturer comes along and proposes a design. The certification approach, at least for noise, would be to find the best fit in Part 36. The long-range goal is that eventually there may be new categories or requirements that actually evolve from the early applicants and the noise levels that are demonstrated for these types of vehicles. So that's the so what, that's the emerging requirements for noise regulation as it pertains to these types of vehicles. I'm going to do a quick review of the GoFly Noise Prize as I understand it. I would like to offer my kudos to the GoFly organization for offering a substantial prize for noise performance. This is indicative that the industry understands that noise could be a barrier issue for the market, and that noise performance should be considered a key parameter in the design. And this is one example of an organization putting the money where its mouth is, so to speak, when it comes to noise performance. It seems like there is a legitimate and substantial noise performance prize. So as all Phase 2 winners are fully aware, the $250,000 prize, noise prize as it relates to noise, is for the personal flying device. It needs to perform the following mission: that it be designed to carry a human operator, at least 200 pounds, and then be able to perform a flight demonstration that would include a takeoff and climb, a speed run of 6 laps around a nautical mile course, would demonstrate an aborted landing, would loiter to ensure that the flight demo is greater than 20 minutes, and then do a descent and landing. The takeoff and climb and the descent and landing would be in the landing envelope that is shown here. And the noise measurements, that part of the flight demonstration, the noise measurements would be conducted during the takeoff from the landing envelope, and then also during the approach and the landing. It's during those times that the noise measurements would be made. The schematic there on the right shows that there are 6 microphones placed around the takeoff and landing envelope. The microphones are 50 feet from the center of the envelope. And then the envelope is described by a cylinder that is 30 feet in diameter, 12 feet high. And the PFDs need to be able to take off and land without violating that cylindrical envelope there. And as I just discussed, the noise will be measured during takeoff and climb, descent and landing. There are 6 microphones around, and at each one of those microphones, the noise is going to be monitored as the PFD flies away and then as it approaches. And a maximum noise level, a weighted noise level, will be established for each one of those microphones. And my understanding is that a noise value will then be made based on the average of the highest 3 microphones, the maximum dBA. From there, for a competitor to be and have a compliant design, the competitors would need to meet the 87 dBA noise threshold. So for that value, that noise value that I just described, it would need to meet an 87 dBA or lower noise threshold, such that the noise score shown here would be at least 0 or a positive number. And so that's for the applicant or the competitor to be a compliant entry. And I should say that the highest noise level for the takeoff or the landing, whichever one is observed, would be the final value. Just a couple of notes that I noted in the technical requirements are that the winds will be less than or equal to 15 knots with gust factor less than or equal to 5 knots. Winds can play a part in the noise generated by these devices. And then just some other miscellaneous things I noted from the technical requirements, that the noise is measured in decibels, a very standard reference to 20 micropascals. It's going to be A-weighted, slow time weighted using class 2 or better equipment. I will say what was not specified in the requirements was the microphone configuration. Would a microphone stand be used versus a ground plane or something like that? And so those are items that I guess will probably be nailed down as we get closer to the demonstration. So previous slide showed the technical requirements for the noise prize for GoFly. So now I want to make the leap to regulatory noise considerations and describe how we would demonstrate noise levels if we were certifying an aircraft for regulatory noise levels and for those considerations. So I'm going to describe that here. It is more complicated, so bear with me. The regulation prescribes a 3 microphone array where the middle microphone is on the center line, the flight track of the vehicle. The other 2 microphones are placed 150 meters on either side of that flight track. And the vehicle then flies over that microphone array, over the center microphone at 150 meters. 150 meters, for reference, it's 492 feet. So it's pretty close to 500 feet. So the regulation says that the noise levels are going to be measured, the third octave spectra standard noise levels are going to be measured. And instead of the dBA noise metric that is being used for GoFly, the regulatory standard is for the perceived noise level metric to be used. It's just a different weighting metric that is applied to the measured spectrum. If participants are interested, the FAA website, FAA.gov, has these requirements. You could read all about the perceived noise level specifications, and I would refer any GoFly participants, if you want to know the A-weighted metric. The NASA GoFly master lecture was had a very good description of the A-weighted noise metric. But that's where we start on the regulatory side, is we get perceived noise levels out of the spectrum. From there, the tone correction penalty is applied, or tone correction is applied to the noise levels. So if the spectra has high tonal content, there's actually a penalty when it comes to regulatory noise. That penalty does not apply to GoFly. The dBA metric does not account for that. So as the aircraft approaches the microphone array, the noise levels are lower at that point, and they increase to a maximum PNLT value when the aircraft is near overhead of the microphone array. And then as the aircraft passes by the array, the noise levels fall off, eventually fall off. To comply with the Part 36 noise requirements, what is critical is that during this flyover, the maximum PNLT value and the 10 dB down points on approach and as the aircraft is retreating from the array, all those values have to be captured during the noise measurement, the max peak and the 10 dB down period. And from there, the effective perceived noise level is computed by integrating the PNLT values just described here over that 10 dB down period. I'm going to add just a couple of notes. The Part 36 requires that the noise levels are captured at every 1/2 second interval as the aircraft flies over. Again, that's not pertinent to GoFly, but that's the requirement, is every 1/2 second interval. So that effectively creates a duration penalty that would apply to noise certification. Again, the duration penalty or the tonal penalty described here, that would not apply to the GoFly noise contest. One other comment I would like to make there is that the regulation prescribes a 4-foot microphone stand, that the microphones be placed on a 4-foot microphone stand. They be oriented with grazing incidents, and they be fitted with a windscreen. That's what the regulatory standard is. Again, those parameters were not specified as it relates to the GoFly prize. Again, if there's more interest there from the participants, what the noise certification part of this can be found on Part 36. And then for the Go Fly technical stuff, the master lecture from NASA Langley is a very good resource I would recommend. So for the EP&L values that I just described, I'm going to discuss the historical noise limits that have been regulated by the FAA. I'm going to start with transport airplanes. For transport airplanes, for that category of aircraft, before 1969, there was no noise limit. It just was not part of the regulation at that time. And so in 1969, thereabouts, when the first noise requirements were set, the stage 1 noise level was drawn probably just right above where all of the noise certification levels had been measured for different aircraft. And that was the stage 1 noise definition. Basically, it wasn't a limit. Measured noise levels were used to define the first stage 1 noise limit. After 1969, the regulations said that any new applicants for this class of airplane had to meet the stage 2 noise level. So there was a more stringent noise requirement that was then required for airplanes in this category after 1969. And then as time went on, airplanes that were designed after 1975 had to meet more stringent noise levels, the stage 3 noise levels. Again, the noise levels were even more increasingly stringent in 2006. And then just here recently, in the last couple of years, the airplanes on the transport airplane side, they're all the way to stage 5 noise levels. So you can see that the noise requirements were very loose at the first when these aircraft were introduced into the market and the public was exposed to the noise levels. And then over time, the noise levels have become increasingly stringent for this category of aircraft. It should be noted that in North America and in Europe, they did ban the use of stage 1 and stage 2 aircraft. That was not an immediate thing that happened when the requirements were established, but over time they did eventually ban the use of stage 1 and stage 2 aircraft. Even though stage 3 and stage 4 aircraft don't meet the latest requirements, they are still grandfathered because they were designed previous to those requirements being established. So that's on the transport airplane side. Let's look at helicopters. Basically, the same thing happened for helicopters designed before 1986. There really was no limit. Stage limit or a noise limit was drawn representing stage 1 aircraft. These were grandfathered if those aircraft were designed before 1986. But any aircraft designed after March 86 had to meet more stringent stage 2 noise requirements. And then more recently in 2014, for helicopters, it's gone to stage 3 noise requirements, so even more stringent. So the takeaway here is that the noise limits are becoming more stringent over time. Eventually, some of the earliest stages of aircraft can be banned from use like they were for transport airplanes in the US and Europe. So far, no helicopters that were previously certified to these earlier levels have been banned from use. But you can see that for new aircraft type designs, they do have to meet more stringent noise requirements. Want to look at, for a helicopter noise requirement, what this looked like for a stage 2 helicopter. The stage 2 noise limit for flyover prescribed in Part 36, you can see there it is a function of gross weight. It's not a single noise limit value, but it is a function of gross weight. The Model 430 was designed after 1986, in the early to mid 90s, I believe was when it was certified. So it had to meet the stage 2 noise level requirements, and the Model 430 met the stage 2 noise level requirement with margin. So it was certified, put into service, and has been on the market since. And then the stage 3 noise level requirement came to be in 2014, and you can see that for the Model 430, if we were certifying the Model 430 today, it would not meet the stage 3 noise requirement. Because it was certified before 2014, someone that owns a 430 can still operate a 430. We can actually still build 430s if we wanted to. Bell made the strategic decision we have just discontinued that product line. But that if we were trying to certify an aircraft today, it would not meet the, for that 430 anyway, it would not meet the latest noise requirements. So let's discuss the helicopter procedures very quickly. I'm going to start off with the flyover condition. For noise regulatory standards, you have to have 6 valid test runs. VH is an airspeed that's prescribed for an aircraft. It's the maximum level flight airspeed at 100% power that it can fly. And so the noise level requirements during flyover, the airspeed is supposed to be 9/10 VH. You fly over that microphone array and you measure the noise like I described a few slides ago. And the aircraft flies 150 meters or approximately 500 feet above the microphone array. The next 2 conditions are the regulatory operations. They are more representative of what the go-fly technical requirements are because they're the takeoff and the approach. For takeoff, again, for all of these conditions, you have to have 6 valid test runs to certify the noise levels. For this condition, you don't fly at 0.9 VH airspeed, but you fly at what's called the max rate of climb speed for your aircraft. So the speed at which the aircraft has the max rate of climb performance, that is the airspeed that you fly during the takeoff condition. At a certain point in front of the microphone array, I believe it's 500 meters in front of the microphone array, the aircraft pulls maximum takeoff power and climbs over the microphone array. And so that is the takeoff condition. For the approach condition, the airspeed again is at that max rate of climb speed. The pilot establishes a 6-degree glide slope at the VY, flies over the microphone array. Part 36 prescribes that the aircraft passes through a point 120 meters, about 394 feet above the microphone array. Couple of notes on Part 36 and how it prescribes these requirements. For the takeoff and the approach conditions, Part 36 prescribes that these operations are done into the wind. For takeoff and landing, on the Go-Fly prize, I did not see anywhere in the technical requirements where it said one way or another, But for Part 36, for our noise requirements, we are, the Part 36 prescribes that those conditions are performed into the wind. My understanding is that those are for safety considerations more than anything else. Part 36 prescribes wind speeds less than 10 knots, and the crosswinds can be no more than 5 knots during any of these conditions. I mentioned before, the noise levels have to be acquired at every 1/2 second as the aircraft flies over the array. Very precise aircraft position and performance measurements must be obtained on the aircraft, and they have to meet tolerances that are prescribed in Part 36, as well as weather data has to be acquired at 10 meters, like temperature, relative humidity, and those meteorological conditions have to also be shown to be within the tolerances prescribed in Part 36. So I'm going to discuss international standards. What I've shown so far is the FAA's Part 36. Noise levels for an aircraft that is 7,000 pounds or higher must have to meet the requirements of Appendix H. Those requirements require 3 flight conditions I just described, 3 ground microphone array, the noise level in EP&L. I just went through all that. The international standards that are put forth in ICAO Annex 16, Chapter 8 is equivalent to Appendix H Part 36. These standards are harmonized between the ICAO and the FAA. So that is something that is very helpful to applicants that are certifying aircraft, that you don't have to certify it one way in the United States and then certify different requirements overseas. Both of the requirement standards also allow for aircraft that are under 7,000 pounds, for helicopters, I should say, under 7,000 pounds, can demonstrate noise levels to a little bit of a lesser standard. It would require only 1 flight condition, the flyover condition, only 1 ground microphone, and the noise level would be measured in sound exposure level instead of EP&L. It is a metric that is like EP&L. The catch here in using Appendix J or Chapter 11 from ICAO Annex 16, the catch here is that there is a more stringent noise requirement to meet if you are showing and demonstrating noise levels to this requirement. So there is, the test is easier for Appendix J Chapter 11, it's less costly. So those are good things, but what you do have to consider is that if you go that route, you do have to have ample margin to ensure that you don't fail the test, because going that route, there is a more stringent noise requirement. I think that's all I'm going to discuss there. There are some, again, emerging noise measurements that have been obtained. What I'm showing here are noise levels that the FAA has allowed to show by permission. These were previously presented at the Urban Air Mobility Noise Working Group, the semi-annual meeting at NASA Glenn. There are several UAS types of vehicles. The first 5 examples there in the table are a fixed wing type of UAS. And then the last 2 are quadcopter, helicopter type design. For the fixed wing aircraft there, you can see that the gross weight of those vehicles varied wildly. for those that are demonstrated there. You have a 13-pound fixed wing vehicle. You got a 46-pound. You tell they're not very large aircraft that have been demonstrated so far. There is one example of a fixed wing aircraft that was 397 pounds. So that's getting closer to like the go fly requirements, that mission. But that aircraft type is, I don't think, a good example of the noise levels that you would expect for a go fly type of vehicle, because that design was a fixed wing configuration. That particular aircraft design did not meet the requirements of, they were shooting for the Appendix G noise level from Part 36. And that design, it's not an optimal design, and it did not, my understanding is it did not meet the requirements of Appendix G for the takeoff condition for Appendix G. If you're comparing what might be most applicable and representative of a go-fly type of vehicle, it would probably be those last two. You've got a quadcopter and a hexcopter type of configuration. The problem is that the gross weight is so low, and you can see the noise levels that were measured there, very low noise levels that were measured for those type designs. It kind of gives credence to the FAA for not requiring a noise requirement for this class of vehicle, because the noise levels are down at the level consistent with ambient noise levels in urban areas. So very low noise levels. The question there is, though, if you're going to compare compare to a personal flying device like GoFly is considering, the question on the table there is whether you can scale appropriately all the way from these small UAS to the vehicles there. That really is the question on the table if you're going to make any comparison here. But those are the noise levels that have been measured so far by the FAA, and so I appreciate the FAA sharing those noise levels with us. So I'm going to wrap it up. In summary, the FAA authorizes small UAS under Part 107. There really is no noise regulatory standard, no noise requirement. Those have been authorized by exemption by the FAA. We are expecting requirements that will be established for UAS and UAM type vehicles. The noise from these vehicles could impact the public acceptance and the success in this market. So developers do need to consider noise to be a key parameter in the design. It is strange to hear someone representing an operator, an applicant, to say that noise regulation may, when appropriate, could actually help prevent a barrier to the market. It actually could be a good thing. The question there again is when is it appropriate? I know that 55-pound limit, it is under consideration. So let me wrap it up there. Again, I want to say to the Phase 2 winners, I want to offer the congratulations. Please accept our congratulations for the accomplishments that are demonstrated so far, the significant technology advancements, and want to offer our best wishes as you proceed to Phase 3. So from there, I'll take any questions.
Thanks so much, Royce. Really appreciate all of that information that you offered today. A question that we have is, can you comment on how the circular array for GoFly compares and contrasts with the linear array you described for regulatory measurements?
Okay. the more I look at the technical requirements for the GoFly Noise Prize, there is merit to the design, the configuration that they've set up here. I think that it's fair, and they have to balance being able to capture the noise requirements, the noise performance of the competitors, but you have to consider the workload and the amount of effort that's required to then process the data and so forth. The comment that I would make as I look at this is that the noise level requirement in the regulatory standard, the aircraft are typically flying over at 400 feet, 500 feet when they pass over the array. GoFly does not prescribe that here. It leaves it to the competitor at what altitude it flies over the microphones, but it appears that the vehicle, the PFD, is going to be closer to the microphones. So that would be really my only comment there.
Okay. The regulatory diagram had distances off the side of the aircraft of 150 meters. GoFly is far closer. So what are the differences? Are there any approaches or techniques that you can recommend for such close measurements?
What I can say is, I mentioned the noise levels that were measured by the FAA for the very small UAS. If the noise levels scale linearly, like you would hope that they would, there's merit to where that noise target, this 87 dBA threshold, there's merit to where that was placed. The question is whether you can scale from very small UAS to the larger PFDs that GoFly has designed. So that's just going to be a question that we're going to have to take a wait and see approach. But to that end, as I look at what GoFly has prescribed here, the placement of the microphones with respect to the landing point, the noise target, I can see merit in what they've, the balance they've had to take in designing a fair contest, but at a reasonable cost to go and process data.
And so, Royce, there's another question related to the microphones you just mentioned. Does the GoFly microphones on the ground impact the perceived or measured noise?
That's a good question. NASA's master lecture discusses this a little bit. If you have a ground plane microphone, you're going to get basically a doubling of the noise level. So if you use a ground plane microphone, the typical practice is that it's understood, well documented, that those noise levels are 6 dB high. So you would take off the 6 dB if you use a ground plane type of measurement. That's my understanding. Again, I refer to the master lecture from NASA Langley. They had a slide on that.
Okay, great. Another question, are there any regulatory exemptions for aircraft aimed almost exclusively at the defense market, like say the Osprey?
There is not a civil, a civil noise regulation for the V-22 Osprey, for instance. But at the same time, the V-22 is not is not certified for civilian operations. And so Bell Boeing, we're teamed together on the V-22 Osprey. We had no incentive to go certify to the civil requirements because that aircraft was not going to be held to the civil standards flying in and out of those areas. Typically, they fly out of in and out of military bases, things like that. So I wouldn't call it an exemption. If you read the requirements of Part 36, there are examples of exemptions for firefighting operations, for I saw a proposal that just came out today or very recently from the FAA where they were proposing to expand some aircraft that would be exempted from noise requirements, but they're public use aircraft and fairly narrow aircraft that would be considered for those exemptions. But yeah, this is a very timely question.
Another question is, how effective is noise canceling? As in a speaker system that sends out equal and opposite sound waves?
Active noise control systems have been shown to be effective on turboprop aircraft when you're considering the noise levels inside the aircraft, inside the fuselage. So for the passengers that are seated inside the aircraft, active noise systems, there are some active noise systems that are baseline on some type designs because the market demanded it, basically. Most cases, they're kits that purchasers would add on depending on the market that they were serving. My experience is that active noise control has not been demonstrated yet to be effective as it relates to the certification noise levels, the noise levels that are propagated away from the aircraft and observed on the ground. I have yet to see an application of noise control that was effective, that would be useful for civil operations. I did see a demonstration, a very limited demonstration over a very specific area. I believe it was a Vertical Flight Society paper a few years ago in the wind tunnel, where at a very specific location, they demonstrated an active noise control benefit at a very specific area, but then it was understood that they probably made it worse in other orientations. So I guess my answer to that is I think that active noise control, where the technology is at today, would have limited application for regulatory noise as it relates to civil requirements.
And to which stage level do you find that the GoFly specification is comparable? And are there regulatory exceptions for aircraft that do not meet the specification?
Those are good questions. Those are very good questions. Let me say this. As an example, as demonstrated by GoFly offering a substantial noise performance prize, it is understood by the industry that noise could be a barrier to the public acceptance and the success of this market. So it is critical for noise performance to be considered a key parameter. Historically speaking, like I described, for new aircraft designs, like transport airplanes and helicopters, early transport airplanes and helicopters really had no noise requirement. Stage one was drawn based on the noise levels that were demonstrated, and then future aircraft had to meet more stringent noise requirements. So perhaps that'll be the same thing in our market. You know, the earliest noise requirements for this, for the new vehicles, it's unclear to me whether a noise limit will apply or not. I don't know. The answer is I personally don't know. What I can say is that if the market is going to be successful, we need to be quieter than conventional helicopters. When you consider that these aircraft are probably going to be flying closer to the public than conventional helicopters, and we want the market to be successful. We want there to be a lot of them, and if that's the case, for that to happen, the noise levels are going to need to be quieter than conventional helicopters. So I guess I'm going to shrug my shoulders a little bit when it comes to that. Historically, a new aircraft type doesn't have a noise limit to meet, but to be successful in the market, I'll stop there.
Okay. Are there blade-mounted devices that can be used to improve the noise of our device? Will they have a performance effect?
I'll say the answer is probably yes and yes. And there are a lot of technical papers out there by AIAA and the Vertical Flight Society that have there's a lot of technical papers that have demonstrated those kinds of things where you might get a noise performance benefit, for instance, but you take a noise performance, or I'm sorry, you take an aerodynamic performance penalty. And so when you're looking at those types of devices, your answer is very astutely stated. You have to look at the noise through the lens of what it does to the aerodynamic performance, because you have to meet the mission, and you want to do it as efficiently and quietly as possible.
And a follow-on to that is, are there ways we can operate our GoFly device that can reduce the perceived noise?
Yes. Yes, there is. I'm a little uncomfortable maybe coaching GoFly participants. I will say that there's some research one could do. HAI has a Fly Neighborly campaign. There are some noise abatement procedures that are documented there. Again, VFS, AIAA, there's a lot of technical papers out there that we'll discuss that. May just take a little bit of research on your part, but I think it would be informative.
And Royce, if you wouldn't mind, perhaps we can follow up with you and ask you for perhaps some links or some reference points that you just mentioned here that we can include in our follow-up to the teams.
I'd be glad to.
Great. Well, thank you so much, Royce. We appreciate the hour that you've spent with us and the incredible master lecture that you've provided to our teams. And we look forward to sharing this widely. Let's see if we can take just one quick question, if you are able to stay with us for a few more moments.
Certainly.
Is there any advantage to taking off and climbing out over one of the 6 mics or between 2 of them?
Directly over versus in between. In between 2 microphones. If you know something, if a competitor knows something about the noise, what would you call it? The noise characteristics of their design and know the directionality that is typical for the design, I would say yes, there's perhaps an opportunity there. The most the least risk associated with that type of operation, if you were going to take that approach, would be you would need to go and take some measurements and look at what the directionality, the noise directionality of the design is before you know base it on predictions or analytics or something like that. That would be something to consider. Again, for us, the regulatory noise standard is we take off into the wind, and we try to keep it pretty stable as much as we can. We try to keep it that takeoff and then the approach. We try to do it as stably as we can.
Well, thanks so much, Royce, for taking that question. We appreciate it. Again, thank you so much for all of this information. We look forward to sharing your lecture as well as some additional resources with the teams. And to our teams, thanks so much for joining us. And stay tuned. We have many more upcoming lectures in May and June, and we look forward to sharing them with you soon. Thanks so much.
You're welcome. Thank you, Nidhi.
Bye-bye.